Okay, should we go?
Yes, thank you.
Okay, can you hear me okay?
Yes.
Yes.
Okay, great. All right. Thanks for inviting me to talk here. I wish I could be in Vietnam. I never visited. I would love to visit, maybe in better times. So today I want to talk about RISC-V, just give an overview of the whole project, why we're doing RISC-V. The title is Instruction Sets Want to Be Free. So I'll dive in and explain why. I always like to start this talk by asking why instruction sets matter. And I always answer this question by asking some questions. Or why can't Intel sell mobile chips? Right? So Intel, big, powerful company, but they've had almost no success in mobile. And the reason is that people want phones and tablets that run the ARM instruction set. But on the other hand, ARM partners cannot sell servers really. So the problem is that people in the server market, they want machines based on the AMD 64 instruction set. So what's interesting here is Intel makes a lot of money selling servers based on an AMD designed instruction set. Intel actually tried to move the industry to a different 64-bit instruction set called Itanium, but that failed, and Microsoft and AMD designed a different instruction set called AMD 64. Intel had to license that, but now they're selling a lot of servers based on that 64-bit instruction set. Also, IBM is still selling mainframes. So the IBM 360 is the oldest surviving instruction set. It's well over 50 years old now. And in fact, IBM, they invented the idea of an instruction set architecture with the IBM 360 line. The idea that you could have a single instruction set and many different implementations. In fact, when they announced the IBM 360, they came out with 6 models on the same day that all ran the same software, but anything from 8-bit to 64-bit data paths inside those first machines. So the instruction set is really the most important interface in a computer because it's where software meets hardware. So it's where the whole software world connects to the hardware world. That's why you can see here, the instruction set basically divides up the industry into segments. Now, everywhere else in computing, there are open interface standards. So the instruction set is an interface. There are many other interfaces, and most of those are open. So for example, Ethernet for networking is an open standard. Anybody can build an Ethernet implementation, and you can have free and open implementations, or you can have proprietary implementations. And same is also true for graphics. OpenGL is an open standard. In databases, SQL is an open standard. In operating systems, the POSIX API calls, they're an open standard as well. So in all these different parts of computing, we have open interfaces, and they're very successful. We build whole industries around them. So why don't we have an open interface instruction sets? That's one place where this has been missing so far. Right, and our answer is, well, no, there's no good reason we should have an open interface there as well. Now, one of the reasons you may say, why does it matter that this interface is open? Well, one of the big issues is if that interface is owned by a company, if it's proprietary, then the existence of that interface is tied to that company's fortunes. And we've seen over the decades, many companies come and go, and they've taken their instruction sets with them. So there used to be a company, Digital Equipment Corporation, very big and powerful. They had some important instruction sets. The last one was Alpha, which was a very well-regarded RISC instruction set that at one point was the highest performance microprocessors. They've gone now and taken Alpha with them. And if your software world was built on Alpha, now you have to go rebuild your software world in some other instruction set. Intel is still selling x86, but they've had a long line of other instruction sets they've tried to push into the market and failed. i860 was Intel's RISC instruction set back in 1989. They pushed that out. And in fact, the first version of Windows NT was written for i860, but that's dead and gone now. SPARC was one of the early RISC instruction sets. It came out of the work in Berkeley in the mid-'80s. What's interesting with SPARC is Sun actually made this an open standard back in 1994. So this was a very early example of having an open instruction set. But then SPARC was acquired by Oracle, and Oracle then closed up the instruction set and then eventually killed all SPARC development. So SPARC is basically dead now. So that instruction set is gone. MIPS is another example, one of the early classic instruction sets. We just heard Professor Amano talking about MIPS. This was one time very popular instruction set, then it went downhill. It was sold to Imagination. then bought by the Wave startup, and now that's going under. Interestingly, in 2018, they said they were going to open up the MIPS ISA, make it open, but then they closed it up again in 2019. And now MIPS is in very big trouble. Not quite sure what will happen to MIPS. IBM Power, this is IBM's proprietary instruction set, but they've now opened this up as Open Power. And they've gone through various stages of how open this is. And finally, ARM. So ARM, is a very big, popular instruction set in the industry. There were some question marks in the industry when SoftBank acquired them and took them private in 2016. And now, of course, the big news over the weekend is NVIDIA is now acquiring ARM. And so there's some uncertainty about what will happen. The main story of this slide, though, is really, this is not a new phenomenon. Companies and their instruction sets come and go. And the real issue is that if the instruction set is proprietary, then its existence and how you can use it is tied to that company's business fortunes. So that's one problem with proprietary instruction sets. Now, a different problem we have is that there are many instruction sets. If you look at a modern SoC, there are many different instruction sets on that SoC. You may say, oh, this is, for example, an ARM SoC. But that usually is only talking about the applications processor, which is the general purpose part of the SoC. Across the chip, there are many other processors on there: graphics, image, radio, audio DSP, security processors, power management processors. And it's not unusual to find that a single chip may have a dozen different instruction sets on that same chip. And each of them has their own software stack. And you might ask, why do you need so many different instruction sets? Well, part of the reason is that the applications processor instruction set is just too big and clunky to be used in these other more specialized areas. It was not designed to work as a specialized, the core of a specialized engine. And so you don't really want to use it in these other places. The other problem is that you cannot use that instruction set and in an IP block that you sell. So most of these other blocks in the chip will come from third-party companies that sell that IP. And they're not allowed to use proprietary ISA as the basis of their IP, so they can't sell it. So they're motivated to come up with their own ISA. And so every IP block with some core in there may have a proprietary instruction set built into that core that you have to deal with. And finally, engineers sometimes just think it's fun to build their own core, think it's cheaper, and they go design their own instruction set. And that's really the worst thing to do, because the real cost is in the software, and maintaining your own software stack is very expensive. So this is why there are so many instruction sets around there right now. The applications processor is not designed as the base for these accelerators, and the licensing terms mean you cannot use it in your IP block that you sell. So you buy IP from different places that had to do their own proprietary instruction set. And also engineers are just building their own cores because they don't want to pay license fees, or they want to tune it for their own use case. So do we really need all these different instruction sets? Do they have to be proprietary? Do they have to keep disappearing? This is a big cost in the industry when ISAs change. So the idea behind RISC-V, what if there's one stable, open, and free ISA that everybody can use for everything? And that's really what we've been working on in RISC-V. So the background is, back in 2010, my research group at Berkeley, we've been doing a lot of projects. I used MIPS and SPARC and x86 and other projects. And we were picking the instruction set to use for our next set of academic research projects. x86 and ARM were obvious choices because they are popular. But both of these are very complicated instruction sets. And also there were IP issues. We couldn't implement them and then share the implementation. That's just not allowed by the IP regime of these instruction sets. Also with ARM, we wanted to work in 64-bit machines. And back in 2010, ARM did not have a 64-bit instruction set. So we decided to build our own one back in summer of 2010. So RISC-V is now 10 years old. The main designers were Andrew Waterman and Yunsub Lee, who were the graduate students working with me and Dave Patterson on this project, building this ISA. We thought it would only take 3 months. In practice, it took about 4 years for us to be happy with the design. But along the way, we did a lot of tape outs, and we ported the compiler, we ported the operating system, we iterated on the design. So it took a while, but we worked pretty hard to improve it. The name is RISC-V, written as RISC-V as a Roman numeral, because it is the 5th major Berkeley RISC ISA. So RISC-1 and RISC-2 are the famous early RISC chips from Berkeley, and Dave Patterson coined the term RISC for these early chips. But then he changed the naming scheme to SOAR and SPUR, and he regrets doing that. So we went back and renamed those RISC-3 and RISC-4. And so now RISC-V is the 5th incarnation. And notice it's RISC-V, even though it's spelled with a V. It's a Roman numeral. RISC-1 and RISC-2 are called RISC-V and RISC-V. They are not called RISC-I and RISC-II, right? So it's not RISC-V, it's RISC-V. One other difference here is RISC-I, RISC-II, 3 and 4, SOAR and SPUR, they were all only a single chip implementation. It was just a one-off research project. But RISC-V has been implemented many, many, many times. What's shown here is the very first implementation, Raven 1, which was done in 2011 in 28 nanometer FD-SOI. But since then, there have been many, many more tape-outs of RISC-V cores. So we decided to push this out. In 2014, we went to the Hot Chips conference, and we tried to make a big splash about RISC-V and introducing it to industry. We had a very positive reception there. People in the industry felt there was a big need for something like this. We had a very positive response. And so we started creating a series of RISC-V workshops for people to attend and give us external feedback on this. But the industry folks, the feedback we got there was they needed something more longer lived, more stable than a university project if they were going to use this. And so in 2015, we created the RISC-V Foundation with Rick O'Connor to provide a nonprofit association to manage the standard. This is now turned into RISC-V International, which is headquartered in Zurich, Switzerland. And RISC-V International is a nonprofit that serves its members and industry. And it's really a trade association that manages the standard. So it manages the RISC-V standard, the compliance suite, and other deliverables. And the goal is to help a central place for the whole ecosystem to grow and to promote RISC-V as an idea around the world. So RISC-V International is taking off in a big way. We have members all over the world. There's a big contingent in China, very interested in RISC-V. In Europe, there's a lot of activity in RISC-V as well. Recently, the European Union has decided to base some of the high-performance computing work around RISC-V. They're funding development of vector accelerators based on RISC-V in Europe. In India was one of the early countries that adopted RISC-V as a national architecture. And the government there has funded 2 major projects developing. One project is developing 6 open source RISC-V cores. Another one is developing high-performance superscalar out-of-order cores for use by the Indian government projects. In Japan, we've had, thanks to Kawasaki-san, we've had great interest in Japan and growing attendance of these events. Thank you for driving this in Japan. In North America, we've had wide adoption. So for example, NVIDIA now uses RISC-V in all of their GPUs as a control processor, the microcontrollers inside all of their GPUs. Western Digital announced they were going to change all of their core designs over to RISC-V. And they ship billions of RISC-V cores a year. And there are many providers in North America as well, and great interest. What's surprising is how widespread the interest in RISC-V is. So actually the largest RISC-V gathering I think that's happened is this one that happened in Lahore, Pakistan. And there's over 3,000 people attended an event about RISC-V. And I think the big attraction to RISC-V, it's free and open, it's available everywhere around the world. And at the government level, there's a lot of interest because it's something every location can have their own RISC-V activity. It's not controlled. They can do whatever they want with it, and they can build their own implementations. So it's very attractive as a global standard. We now have many members in RISC-V International. A lot of the very biggest names in computing are involved. For example, IBM, Google, Qualcomm, NVIDIA, Samsung. Many companies involved in RISC-V. It's like a who's who of the computing industry. And a lot of these are very actively engaged in doing projects around RISC-V. The membership has been growing very rapidly across all parts of the industry. Everything from software firms down to foundries are involved in RISC-V. And also universities and academia and research institutes are also involved. Many countries around the world are working on RISC-V. So how does RISC-V work? I can talk about the ecosystem a little. So at the center sits RISC-V International. So RISC-V International manages the specification. The specification is the standard. And this acts as the interface between software and hardware. I think one mistake people make when talking about RISC-V is not an open source processor. That's an incorrect phrase. RISC-V is an open specification. So the specification is open. Because it's open, it means you are allowed to build open source cores. So the implementations, there are many open source cores available for RISC-V from many places, many locations around the world. Different groups are built and supporting open source cores. but the spec itself is the main thing, and it's an open spec. It's also allowed to have proprietary cores. And so there are many proprietary core providers that have their own implementations. And these are implementations you license. You have to pay money to use these. But the companies guarantee the cores. They provide support. They support the customer in integrating these into SoC designs, just as with any other proprietary soft core. The difference here is that with RISC-V, there are many suppliers all to the same standard. And so RISC-V already has more proprietary core providers than any other instruction set in history. And the number is growing slowly over time. And finally, the spec is open, so companies can build their own cores. So for example, NVIDIA, they develop their own RISC-V cores that they use internally, and that's fine. They can do that. And they can share all the software everybody else uses. Western Digital is also designing their own cores. Alibaba is also designing their own cores. So this is where you get the freedom of choice. You can choose to use an open source core. You can license a proprietary core, or you can design your own core. And all these are perfectly valid. Everybody effectively has an architectural license that lets them build the cores. So that's the hardware side. And the great thing about all these hardware implementations, they have a standard interface to software. And so they all share the same software ecosystem. So on the software side, there's been great uptake in the open source community. So all the major open source projects have RISC-V as a supported mainstream architecture. For example, GCC, Linux, many other open source efforts are embracing RISC-V and supporting it upstream. And a lot of the companies involved in RISC-V are helping support these efforts in the open source repositories. But it's not only open source software. There's actually a large involvement of proprietary software companies as well. So companies like Lauterbach, Sega, IER, these folks provide tools for people doing development projects. And these are commercially licensed software that you have to pay for. And this is really a symptom of there's a lot of activity and in big companies, and they're used to having these tools. And so that demand is driving this supply from these proprietary software makers. Engineers want to use the same tools they used to, and these companies are now supplying that for RISC-V projects that are going on at these big companies. So what's different about RISC-V? It's just another RISC in some ways. As you just saw, it's very similar to early RISCs, but we made it simple. We focused on making it a very simple base ISA, and that actually took a lot of work. We made a very clean design to separate out any issues about the microarchitecture. For example, the reason we don't have a branch delay slot is that would expose the microarchitecture to the instruction set, and it'd be very bad for more high performance designs. That's an example of what we left out to make it a clean design. It's a very modular ISA, so we designed it. The whole project that we based RISC-V on, we built RISC-V for, was all about customized accelerators. So we wanted to have a small standard ISA to which you could extend it with only the things you needed. So remember the issue with many ISAs in one SoC, all those different accelerators, they want a sort of standard base so they can run standard software, C compiler, for example, but they want to extend it in different ways for the different application spaces. And so we made it a modular ISA, so you can just add the modules you need to extend it out. One other thing is, because it's an open standard, we're very keen to make it be stable. Commercial companies are often motivated to keep adding features, so they force you to pay for the next version, for the next license. But for us, the community wants stability, so we just freeze an extension once we develop it, and we don't keep changing it. To increase functionality, we just add another module, another extension, instead of changing the version of the things that are mandatory. Another big difference, it's community designed. It's not designed by one company, it's designed by the whole community. And so we can pull in expertise from all of industry, all of academia to help develop this, and also work directly with the software community to put the features in they need to make the software work. So there's a lot of activity at RISC-V International. There are many groups working on many different extensions and extending RISC-V in many different areas. There's great demand to use RISC-V everywhere, and so a lot of features need to be added. And there's a large set of working groups and large number of members with their engineers are working on this. In education, RISC-V is spreading quickly throughout education. The textbooks, the Tennessee and Patterson textbooks, are now based on RISC-V. The RISC-V Reader, done by Dave Patterson, Andrew Waterman, has now been translated into many languages as an introduction to RISC-V. And all the top schools are developing curriculum and material around RISC-V, and this is now being shared through all the schools. And so in a few years, I think you'll find that almost any computer engineering undergraduate will be learning RISC-V in their school. And so this really impacts industry, because people will be coming out into industry having learned RISC-V in their schools. So why is RISC-V so popular? I think engineers sometimes don't see the forest for the trees. They'll sort of fixate on, this is not all about some benchmark being a bit faster or some implementation being a bit lower power. That's not why RISC-V is happening. It's really the change in the business model is why this is popular. In the old days, you had to, if you were building an SoC and you needed a core for that SoC, you would first go to the vendors and have them compete. And then when you picked a vendor, you would get their instruction set, and then they would be able to lock you in to their core for the next generation. With RISC-V, what happens is you say, I'm going to use RISC-V. You pick the ISA first, and then you can have vendors compete for that socket. Or you can build your own core, or you can use an open source core. So you already have that freedom of and competition about the cores you can use in your own designs. Another advantage is you can just go modify RISC-V, add your own extension without asking permission. Everybody has an architectural license. They can do what they want with the core design. So this is really the difference. This is why there's so much momentum behind RISC-V. People see this new business model as being how they would like to operate in the future. And so as a result, there's a lot of investment going into RISC-V. So if you think there's some implementation feature missing, or there's some PPA design point that it's not there right now, for example, very high performance, very low power, if that's missing, somebody is probably working on fixing it right now and investing in that, because they see the new business model as being the way they want things to go. So our goal is really to become the industry standard ISA for all computing devices. We've been saying this for a while, and it's becoming more true over time. So one thing I want to do just at the end of the talk is talk a little about how RISC-V is used in domain-specific computing. We spend a lot of time in this portion of RISC-V the last few years bringing up the general purpose piece, but it started originally as an ISA to use in application-specific processing. As I mentioned, we wanted to have a small base, but this base had to be complete enough that you could run a full C compiler and software stack. And so we view this as giving you a minimal skeleton with a working software stack, and then you can start adding your own extensions. So you can get off the ground with a minimal set while having all the full software support, and then you can add the support you need for your own extensions. And again, there's no permission needed to add your own extension. But we are working on standard extensions. The whole big one that's important in the domain-specific computing is the vector extension. So the vector extension is a major addition to RISC-V that provides vector length agnostic SIMD support. So it adds 32 vector registers, but the length of those vector registers is implementation dependent. So you can have very short vector registers in some implementations, very long ones in others, but all the software can be written so it can run across any vector length. And the ISA is designed for sort of the new world where there are many different data types, mixed width, narrower precision, mixed precision operations. Those are all supported in the vector instruction set. And so this is a very big major project that's getting close to being completed now. And one thing about this vector extension, I'll just emphasize, it really is designed to cover a very wide range of design points. So the very simplest design may be an in-order processor with only a 32-bit wide data path. But there are people already working on very large vector unit designs. The European Union projects are working on a system that has each vector register 16,000 bits of state, and it's operating on many bits per cycle. So this is the range of things, but the goal is all of these different implementations can run exactly the same compiled binary code through the instruction set design. One thing I'll talk about is how you add custom stuff to RISC-V. So the foundation defines the standard ones. We also reserve space that will eventually be used for future extensions, but a portion of the space is left to be custom, and that's space that we will never use for anything standard. And that's where you can add your own stuff without worrying about conflicting with anything that comes later from the foundation. And so, for example, if you think about the encoding space, if this is the reserved encoding space and there's a custom encoding space, when you're coming to do an application, you may choose to add these modules in that are the standard modules, the base instruction set, multiply, atomics, single, double precision floating point. But then you add your own custom instructions over here. Now, the way this works is all the standard software only uses the standard encodings, and so it doesn't care about the custom encodings over there. And so you can reuse all the standard software, but then you can, in addition, add your own libraries that drive those custom instruction extensions. So people worry about, is RISC-V going to fragment? Are there going to be 100 different RISC-Vs? I think it's important to distinguish what I call fragmentation from diversity. So fragmentation is when you do the same thing two different ways, and that is bad. And so, humanity has managed to have two different ways of putting the steering wheel in cars. You have left-hand drive and right-hand drive. That's fragmentation, and that's a pretty bad thing. It means we have twice as many kinds of cars to worry about. But diversity is when you need to have a different problem to solve. Going across town, one person, bicycle may be a great solution, but carrying 500 people across an ocean, a jumbo jet is a much better solution, right? These are different problems. And so naturally, you want to support different solutions to those different problems. So RISC-V is really designed to help you with diversity while avoiding fragmentation by having a common standard. Another way it avoids fragmentation is there's two very powerful forces people forget about in fragmentation. One is users. So the customers of RISC-V, they don't want to repeat a vendor lock-in. They want to make sure all the vendors and everybody is using the same standards. They don't have to worry about being stuck with one vendor. And the second one is software. So the upstream software stack is designed to the ratified standards. And so if your design does not work with the upstream standards, then it won't be usable by most of the customers. So these are two powerful forces that stop people from fragmenting RISC-V. Okay, so I'll just wrap up here. So RISC-V is really about completing this innovation cycle by having an open ecosystem. Education, industry, research can all use the same ISA without any constraints on sharing. And it means you can quickly transfer ideas from universities to industry, and you can quickly have industry problems moved into universities for them to work on and train university researchers to use the same thing. The same simple thing they learn in classes is actually the thing they'll use out in the real world. Okay, thank you.
Okay, thank you very much, Professor Kasunbowo. And I get one question from audience chat. And the first question is, what is the quality of the free open source RISC-V IP cores?
What's the quality of the free open cores? It varies by the core. There are many different cores. Some of them are commercial quality, some less so. Some are research projects. Some are basically commercial companies providing an open source version. So it does vary quite a bit. But there are many of them. So you get to choose and look around at all the different open source cores out there.
Okay, thank you very much. And second question. When do you think that 128 bits ISA will become popular?
I think as large data centers have very large solid state memories connected over networks, that'll be an application. So very large data center applications. Already you see petabytes of storage. So people already need more than 50 something bits to address that. And they would like to have very quick access to network detached solid state memory. So I think that is the place that you'll see the need for 120-bit addressing first, is very large data center clusters or very large databases held in solid state memory. I think that's, I think another 5 or 10 years, people will be hitting the limits of 64-bit addressing. And that's when they'll start looking at the 128-bit, I think.
Okay, thank you very much. Oh, a third question from Mr. Hong. Would you teach me what's the main difference among RISC-V, ARM, and ARM64 ISA?
Big difference is the business model.
Big difference.
It would take many hours to go over all the other detailed differences, but the first thought of the biggest difference is business model.
Okay. Oh, and And next question, if the ARM and ARM6 ISA are not opened, so how the vendor understand its interface for using?
Sorry, I didn't understand the question.
This one?
Yes.
Okay. So it says, if ARM and AMD 64 ISA are not opened, how the vendor understand its interface for using? From Mr. Hong. But
so the instruction set is, yeah, so people can read the spec and port software to the instruction set. You are not allowed to build an implementation and even give it away. You cannot build an x86 implementation and give it to people. You cannot build an ARM implementation and give it to people. Licensing rules do not allow that. So you can port software to the interface, but you're not allowed to share an implementation of the interface.
Okay.
Okay. 見えてます?
Okay. 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 Next question.
Okay. Yeah. Okay. So the next question is, was it the Chisel's modular design that allow you to continue research and development of many RISC processor architecture in University of California? What are the main? Yes, go ahead.
Yeah, no, Chisel was developed at the same time as RISC-V, really somewhat independently. But yes, it allowed us to make very flexible core generators, so we could try lots of different ideas out. To be clear, there are many RISC-V implementations that do not use Chisel. Only really the Berkeley implementations are based on Chisel. But we find that very valuable in a way of quickly building different kinds of cores in the university environment. We're also using Chisel at SiFive, the company, as well, to build all the cores at SiFive.
So there's one more question about Chisel. Let's see. What are the main benefits of Chisel that you bring directly to architecture study and then implementation?
Right. So Chisel is meant for writing RTL. So it's one thing to be clear. It's a high-level synthesis language. It's a high-level programming language that lets you write RTL in a flexible way as generators. And so we can, for example, quickly change parts of the design and generate the Verilog. It would be very tedious to edit the Verilog directly. We just find we need many fewer lines of Chisel to do things, and we can quickly add new features to cores using Chisel that we couldn't do easily in Verilog. Another reason we created Chisel actually was Verilog is not standard. Every tool implements a subset of the features of Verilog. And so when you're trying to actually use the more advanced features of Verilog, you find you keep tripping up over this tool does not do this feature, that tool does not do the other feature. And so you end up, like with System Verilog, only using you have to pick a subset that actually works with all the tools. And so a lot of the more advanced features of System Verilog are not actually usable. And so Chisel gives us, all these high-level features we can use, and then we generate very plain Verilog out the back, which tends to work very easily with all the standard industry tools. So we also used it to hide the problems with Verilog implementation and tools. And also we've been using it now to build a lot of other infrastructure. So a project at Berkeley called Chipyard is building a whole SoC design, experimentation, research platform that's based around Chisel. So I encourage you to go look at the Chipyard project from Berkeley.
Okay, thank you. So it's time, and this is session is end. Thank you for Professor Asanović and everyone. Any question? And thank you.
Okay, thank you.